Welcome all of you. In this lecture, I'm going to introduce field extensions to you. So let me start. So let me first of all start with the definition of field. A field is nothing but a non-empty set F which is an abelian group with respect to our addition as well as multiplication. But in case of multiplication, we take care of removing 0 from our set. At the same time, it should satisfy distributive laws for any x, y, z in F. Those distributive laws are given as this: x dot y plus z should be equal to x dot y plus x dot z, and x plus y dot z should be equal to x dot z plus y dot z. So in short, if we summarize the definition of field, we can say that a field is nothing but a non-empty set F which is a abelian group with respect to both addition as well as multiplication. But in case of multiplication, we take care of removing 0 from our set, and this set should satisfy these two distributive laws. So now let me switch to some examples of fields. Real numbers, rational numbers, complex numbers are some examples of field, because any of these set at random, if checked, we can find out that real number is an abelian group with respect to addition. If we remove 0 from real number, then it's multiplicative group which is abelian, and at the same time real number satisfies these two properties. Same can be checked for rational numbers and complex numbers as well. After this, let me move to the definition of field extension. Suppose K and F are two fields such that K is a field larger than F, or I can say that K is a field containing F as a subfield. Then I can say that K is an extension of field F. So let me focus on some of the examples here. Already I have told you the example of fields R, Q and C. So I can say that R is an extension of Q because R is a field larger than Q. At the same time, I can say that complex numbers is an extension of rational numbers. On the same lines, I can say that complex numbers is an extension of real numbers also. Now let me introduce vector space to all of you. What do we mean by vector space is nothing but let V be a non-empty set and F be any field. So V is said to be a vector space over F if it satisfies some conditions. What are those conditions? So those conditions are this. First condition is that V should be a abelian group with respect to addition. Secondly, scalar multiplication should be closed. What do I mean by scalar multiplication is closed? Let me tell you. So let me explain you what do I mean by scalar multiplication is closed. Suppose V is your non-empty set, F is a field under consideration. If you are choosing some element V from V, and if you are choosing some scalar C from your field F, then multiplication of both C and V should be again in V. Then only we can say that scalar multiplication. Last condition for it to be a vector space, it should satisfy these four conditions. So let me give you an example. Real numbers is a vector space over rational numbers, but rational numbers is not a vector space over real numbers, because as I said you in the previous discussion that scalar multiplication should be closed, but in case of this example scalar multiplication is not closed in vice versa condition, because if I take 1 as element from Q and if I take root 2 as element from real numbers, then multiplication of these two numbers does not belongs to Q again. So I cannot say that Q is a vector space over real numbers, but I can surely say that real numbers is vector space over rational numbers. In short, I can say that every field is a vector space over its subfield. Let me tell you in short what do you mean by basis of a vector space. So suppose V is your vector space over F and B is a subset of V. There are two conditions under which I can say that B is a basis of V. The first condition is that B should be linearly independent itself, and secondly B should generate vector space V over a field F. Let me clear my idea by using some examples. Here I have taken a set R square, that is set of an ordered tuples, ordered pairs we can say, and I have taken a field as real numbers itself. So I can say that this particular subset B, that is equal to 1 0 comma 0 1, is a basis of that vector space R square over R, because first of all that set is linearly independent, because you cannot express 1 0 in the linear combination of 0 1, or you cannot express 0 1 at the linear combination of 1 0. So they are linearly independent. And secondly, any element from vector space can be written as a linear combination of these two elements. But if we'll go to the next, then 1 0 comma 5 0, this set cannot be the basis of R square over R, because 1 0 can be written as 1 upon 5 times 5 0, and 5 0 can be written as 5 times 1 0. Now let me come to the final discussion of my lecture, that is degree of field extension. So let K be a field extension of F. I have already told you what do you mean by field extension. K is a bigger field than F and it contains F. Then already I have told you that every field is a vector space over its subfield. So obviously K is going to be a vector space over F. Then it must have a basis. The number of elements in the basis of K as a vector space over F is called as degree of extension of K over F, and it is denoted by a symbol which is given here in square brackets K colon F. This particular symbol denotes the degree of extension of K over F. Let me conclude by some examples. I already told you complex numbers is an extension of real numbers, and degree of extension of this particular field extension is 2, because complex numbers can be generated over real numbers by using just two elements, that's 1 and imaginary I, because any complex number is in the form a plus bi, that is I can say a into 1 plus b into I. So 1I forms a basis of C over R. So that's why the number of elements in the basis is 2. So that's why degree of extension of complex numbers over real numbers is 2. Let me conclude it by another example. Degree of extension of real numbers over rational numbers is infinite, because real numbers does not have a finite basis over Q, or in short we can say that real numbers cannot be generated over rational numbers by some finite set. So I hope you must have got the concepts of field, field extension, vector space, basis and degree of field extension. Thank you so much for listening.